Dear students, welcome to video lecture course Theory of Computations. Continuation to the previous video lecture. In this video lecture, we are going to discuss about non-deterministic finite automata. And this is Dr. K. Praveen Kumar, Assistant Professor, Department of Information Technology. So, as we have already discussed, the prescribed textbook is John E. Hopcroft, Rajiv Motwane, and Jeffrey D. Ullman. Introduction to Automata Theory and Theory Languages and Computations. Textbook purchasing is mandatory. And today's topic is non-deterministic finite automata. Lecture level learning outcome. After completion of this lecture, you will be able to apply the basic concepts of NDFA or NFA on the given string. As we have already discussed finite automata, automata is a 5-tuple automata. And in the previous video lecture, we have discussed about deterministic finite automata. And in this lecture, we are going to discuss about NFA or NDFA. NDFA or NFA is also a 5-tuple automata. And Q, capital Q, is a finite set of states. And sigma is the input symbols. And transition function is different comparing to the DFA and NFA. So the transition function is Q, the number of states over input symbols will give you 2 power Q states. But whereas in NFA, there will be only one new state. But here, there may be multiple new states. This is the only difference between DFA and NFA. In DFA, for a particular state, if you are giving one input, you will get only one new state. But whereas in NFA, on a particular state, if you give one input symbol, there may be a multiple states. That is the difference between NFA and DFA. So the general explanation of NFA is finite automata are called NFA when there exist many paths for a specific input from the current state to the next state. From the current state to the next state. So it is easy to construct NFA than DFA for a given regular language. So every NFA is not DFA. Every NFA is not DFA, but each NFA can be translated to DFA. Each NFA can be translated to DFA. NFA is defined same way as DFA, but there are two exceptions. One is NFA contains multiple next states. NFA contains multiple next states and it contains epsilon transitions. NFA contains epsilon transitions. So this is the example of NFA. For the Q naught is a starting state. For the Q naught, if you give B as input, it may be a self loop and you may get the new state Q1. So on Q naught, if you give A, it may be the next state will be Q naught or Q1. For the Q naught, if you give A, the next state may be Q2 or Q1. So this is, we cannot determine the next state. That is what non-deterministic finite automata. So this is the formal definition of non-deterministic finite automata, which we have discussed in previous slides. So coming to examples of NFA. So now Design an NFA with the input symbol 0 and 1, accept all strings with the 0, 1. So that means that the input symbol is 0 and 1, all strings ending with 0, 1. That is, either it may be 0, 0, 1 or 1, 0, 1 or 1, 1, 0, 1, like, and so on. 0, 0, 0, 1, and so on. So whatever the string it may be, if it ends with the 0 and 1, that must be accepted by the machine. For that, you have to construct the NFA. So just pause this video and try to construct the NFA. So the general NFA will be like, so whenever it has given a zeros and 1, 0 and 1 is the given input string. That is the condition. So you have to take a state Q0 and give an input symbol as 0, and it will go to the state Q1. And if you give 1 as input, and that must be the final state Q2. And coming to this condition, if it is a 0, 0, 1, so you can write here it has a self loop 0, 0, 1, and if it is a 1, 0, 1, then you can also add 1 here. Then if it is 0, 0, 0, 1, 0, again 0, then 0, 1. So it is almost, it is satisfying all the input symbols. So the given language is accepted. Now check the solution, right? So 0, 1, and this is self loop 0, 1, and you will get the final state. The next example is design an NFA over input symbol 0, 1, in which double 1 is followed by double 0. Double 1 is followed by double 0. And take the different input strings or languages and try to draw the NFA and pause this video and try to complete the design. So the solution for this one is, this is the one. So double 1, 1, 1, 0, 0, 1, 1, 0, 0, and whatever the substring or pre-string are 0, 1, 1, 0 are the same after this string also. This will be satisfied here if you give 0 and 1 as self loops here. Self loops here. So it is going to satisfy whatever the string which satisfies this condition. So this is another example. A substring is 1110, and this is the solution 1, 1, 1, 0, and before 0, 1 and after 0, 1 are the self loops. And accept design an NFA over 0 and 1, accept all strings which third symbol from the right end is always 0. Third symbol from the right end is always 0. So this is the solution for that. You check with all the, you try to give all the input strings onto the machine and check the perfection. Right. So having completed the discussion on structural representation, students will be able to define and identify the strings accepted by the finite automata. And this is a lecture level practice problem. And to test whether you achieved this learning, you should be able to solve the LLP. So LLP is construct NFA whose job is to accept all and only the strings of zeros and ones that ending with 0 and 1 is LLP, and convert the non-deterministic finite automata to deterministic finite automata. Convert the NFA to DFA, the following NFA. That must be end with 2 strings. So this is all about this lecture. We'll meet with some other concept in the next video. Thank you.